Yeah, you may notice that I extended the time for the exam. Uh, I realize that this course is on your time, but I also voluntarily give these lectures here, Zoom lectures, because there's some people that actually need somebody maybe to explain things. And so having said that, we haven't done chapter 3 yet, I extended the time to Saturday. So it opens today, and if you're comfortable with it, feel free to jump in and knock it out. Or not wait until we're done with this chapter 3 and then, go ahead and knock it out tomorrow. The other question that comes up is with respect to the time. Here, I got one more here. The time spent on the question, and what it does is basically Canvas logs when somebody, goes away from the browser. And that's for us as a tool to tell us, well, maybe you're out there looking some stuff up. Now, I don't pay a lot of attention to it when you guys are doing activities and homework, but I do look at it real close when the exam's done. It does not infer that you're out there cheating. It's just something we look at. That's all. Okay. That's the only tool we have because we're online here. And sometimes what happens is if you're asked a question, and it's happened quite a bit, and to type in your response in your words, we get a lot of stuff that has been taken directly from websites, and it deals with topics that, way beyond the scope of Chem 130. Doesn't mean that you're not familiar with that, but when I ask a question, explain to me Brownian motion, and I don't get a response, that infers that maybe that was copy and pasted over. So we look at things like that, okay? So don't take offense if I look at it and I say, hey, there's an area here, what's going on, okay? It's not inferring that you're cheating, it's just, just a tool. I've yet to use it to give anybody a 0, let me put it to you that way. All right, so let me see, I got a couple of chats. Okay. Oh, okay, student, which is Kimberly. Okay. You're allowed to change your name, by the way, if you want to change your name up here. So, any questions so far? Any comments, concerns at this point in time? Well, welcome back. Like I said, I appreciate the fact you do come back here and listen. Hopefully I don't bore you too much. But I do know that next semester, this is going to be live. So it's going to be like, we're going to be online, but it'll be live online compared to this semester that is classified as on your time. And that's why all of the assignments, with the exception of the homework, not the homework, the exams, are opened up. So if you want to go finish up everything in the week, feel free. No one's going to stop you from doing it. The only time is the exams. We kind of do it all one time period. Okay, well, chapter 3, that's where we're at. Okay, and I'm going to begin with chapter 3. Now, we talked a little bit about units and so forth, but in this chapter, what we're going to do is use a technique to convert from one set of units to another, specifically English units to metrics. Initially, we're going to stay within the units, either metric or within the English, and then we're going to do a cross. Now, this technique of setting it up properly is there to help you when we get to the chemistry part, when we are doing calculations with respect to reactants, and we try to calculate how much product we're going to make. We're eventually going to get there. And we utilize this technique. To me, there's a special name for it, but I just simply call it, track your units, because if you set that problem up properly and you follow the units and you cancel things out and you end up with the units that you're looking for with respect to the question, you got it set up properly. Now it's a matter of just plugging in the numbers in the calculator and getting your answer, okay? So What do we use with respect to length, mass, and volume? Well, as far as the metric system is concerned, the basic length is the meter. I'm sure you all are familiar with that. And for mass, the basic unit is grams, and volume is liters, and English and metric uses second in both cases. So the symbols there are given to you there in the far right column. Lowercase m for meters, lowercase g for grams, uppercase L for liters, and obviously lowercase s for seconds, okay? Now, we use prefixes. Again, we're talking about the metric system. Kilo is 1,000 times greater, okay? Deci is 10 times smaller. One way to remember this is a little guideline is think about how many years in a decade. There's 10 years, okay? So it's 10 times smaller. Centi is 100 times smaller. So again, another way to remember this, how many years in a century? That's 100 years in a century, right? So the prefix cent, or 100 times smaller. In milli, the lowercase m is 1,000 times smaller. How many years in the millennium? You may not know that, but there's 1,000 years in one millennium. Now, the new one that you may not be familiar with is what we call micron, or micron. Is that symbol looks like a U with a little tail there in front of it? That is 1,000,000 times smaller. So what I want to do is share, I think I sent this to you because I did send it to all my sections. It's a Word document file of a table where I set up the mass, the volume, and the units, okay? And the nice thing about the metric unit that we can go from mass to unit as far as prefixes and without too much of a problem. I said a kilo is 1,000 times greater. So if we look at the mass column, 1 kilogram, there are 1,000 grams. For deci, there's a decade, 10. For 1 gram, there is 10 decigrams, and 100 centigrams, and 1,000 milligrams, and 1,000,000 micrograms in 1 gram, okay? We can take those prefixes and letters and transfer them over to volume and do the same thing. 1 kiloliter, there's 1,000 liters. 1 deciliter, 10, centiliter, 100, milliliter, 1,000, and finally 1,000,000 microliters in a liter. Progress it over to length, which is meters. 1 kilometer, okay, there's 1,000 meters. There's 10 decimeters in 1 meter, 100 centimeters in a meter, and 1,000 millimeters in 1 meter, and 1,000,000 microliters in a meter. Now, every one of these is a conversion factor, okay, every one of them. And being a conversion factor, they're a ratio. So I can write them one or two ways. For example, one kilogram, there's 1,000 grams. I could write it with kilograms in the numerator and 1,000 grams in the denominator, or vice versa, okay? Because which one I use depends on the units that I want to eventually end up with. So if the question asks for, if you're given grams and you want to get to kilograms, well, I'm going to use the setup on the left, because eventually I'm going to set it up so I can cancel grams out and leave me with kilograms. If I'm given the problem is giving me kilograms and I want grams, then I set it up with the unit on the far right, because again, my units kilograms will cancel out, leaving me with the units grams. How do we set that up? For example, question may be asked, all right, how many micrograms in 0.125 kilograms, okay? And so we write down what we're given, 0.125 kilograms. And I know from the conversion factors that in 1 kilogram, there are 1,000 grams. And I set up my first conversion factor such that I cancel out my kilograms, leaving me grams on top. Now, if I just stay with the first conversion factor, unit-wise, I'm left with grams, but the question is asking for micrograms. So I need one more conversion factor. And that's my second conversion factor that I have there. And I set that up again with grams in the denominator. Why? Because I want grams to cancel, leaving me with micrograms in the numerator, because I know there's a million micrograms in 1 gram. So I follow my units. Units cancel out properly. Finally, I'm left with the units that I'm looking for with respect to the question. Because the question asks, how many micrograms are in 0.125 kilograms? Now, the math is up to you. Plug in the numbers, okay, because you check your units and everything's fine. And it's a matter of taking 0.125 and multiply by 1,000 and a million, and you end up with 125 million micrograms. Check your sig figs. Those units, conversion factors, are exact numbers. Now, there was a comment in the textbook that says that exact numbers are not utilized for determining your significant figures because they have an infinite number of significant figures. What that means is that 1,000 could be written with 1,000.00000000 all the way to infinity. The same with a million 1,000.0000 all the way to infinity. Even the number 1 could be written to infinity, 1.00000. Therefore, because they have an infinite number of significant figures, they're classified as exact numbers and do not play a role in determining the significant figures at the end. Which another question was brought up with respect to the significant figures. We spent a lot of time talking about significant figures. Okay, so we use significant figures we will use it throughout the semester. Okay, so and the bottom line with respect to sig figs is I think straightforward, and if it's not, let me know and I'll see if I can address it a different way. But the point of sig figs is saying that you can't write down a number more accurate than the numbers you started off with, whether you add, subtract, or multiply and divide. Now, we broke it down separately when we talked about adding and subtracting. Keep track of your decimal places. And when you're doing divide and multiply, keep track of your sig figs. Okay? So they both are saying the same thing at the end, saying that you cannot present a number that's more accurate than the least accurate number you began with. Okay? That's the whole bottom line. So I know you can plug a number in and give an infinite number of numbers, 1.32148, whatever. But reporting those numbers, what you do, you're adding accuracy to your number that you didn't have to begin with. Okay? Because you were governed by the accuracy in the numbers that you have. If I use this example a lot, if I have a meter stick and I want to measure a given distance, and that's one tool, and I have a second tool that I can measure that same distance with a laser beam. Well, obviously the laser beam is going to give me a little more accurate number. Okay, they both have uncertainty at the last number, but the laser beam is going to give me a lot closer, more accurate number than the meter. And if I use those two numbers to do a multiplication or addition, then the number I end up with, or whatever function I do with those two numbers, one with a meter stick, one with the laser, my answer should be no more accurate than the accuracy of the meter stick, because that is the least accurate tool that you use to measure. Okay, and that's the bottom line with respect to significant figures. So if that's still a problem, let me know, and I will try to find a way to readdress it. Look at the videos, not only the ones I record here, but on the website, there's a video by Dr. Kim talking about sig figs. Maybe maybe having to present in a different form, a different manner might help. Or go to YouTube, type in significant figures. There's tons of YouTubes done by other people explaining it. Maybe it's a different way of explaining it, makes it clearer. All right, now in the shapes table, it's one of the tables that you should download and print out, because you will use that quite a bit. There are 3 conversion factors that convert you from English to metric, okay? And 1 inch is equal to 2.54 centimeters. 1 pound is 454 grams. 1 quart is 946. Now, if you ever have to use those conversion factors, use the ones that we supply. Why? Because if you do go on the internet, you're going to get numbers with a bunch of significant figures, and that's going to mess up your answer. So stick with these conversion factors if you're going from inches to centimeters, and take that further to meters or whatever you need to, whatever that unit. Okay? Use these conversion factors. Now, of these 3 conversion factors, only one of them is, by convention, is defined as exact, and that is the first one. Okay, so this one right here is defined as an exact number. Now that's open to argument, but I want to be consistent with convention because that is measurement, but it is treated as an exact number, okay? Therefore, it would not be a factor if you use it with respect to converting as far as sig figs are concerned. The other 2 are measurements and therefore are not exact numbers. Therefore, they could be a factor in your sig figs if you use them. In fact, there is a homework problem that you need the 1 quart to 946 milliliters. The numbers begins, I believe, with 4 sig figs, and some students have given the result as 4 sig figs, but in reality, the 946 has 3 sig figs, so your answer should have no more than 3 sig figs because the 946 is not treated as an exact number. It is a measurement, okay? Now, the point here is that these conversion factors can be written as a ratio, and they're shown here with, for example, the first one, 1 inch in the numerator, centimeters in the denominator, or vice versa. All of them can be written in that manner, okay? And you can set up the problem such that depending on the unit that you're looking for, you set it up. If I want inches, then the inch stays in the numerator, obviously, okay? Now, why do we want to do this? Because if I go back, let me go back to the previous example we just did, where we had 2 conversion factors. That, to prepare you, is potentially a chemical reaction where these conversion factors could be a ratio of reactants, okay? And we can set up 2 or 3, at the minimum 3, we can go up to 4 of these factors when we talk about chemical reactions. And there, like we're doing here, keeping track of your units will assure you that you have set it up properly to the units that you're looking for, and all that's left is just do the math. Okay, so any ratio can be set up in this system. Even if you have 50 miles per hour, I can set it up as 50 miles per hour or 1 hour per $50. If you have a velocity, 100 miles per hour, same scenario, okay? Now, sometimes one is tempted to change the math. In other words, take the inverse of 2.54. My recommendation is leave the number 2.54 as is, whether it's in the numerator or the denominator, okay? Because that can confuse the thing. So keep it like it is and just flip it over as needed. Okay, so as far as algebra is concerned, yes, we're going to be using a little bit of algebra, but it's a matter of keeping units. An example here would be like a squared divided by a. A squared is nothing more than a times a. So I can separate it, and you can see here my a's cancel. So unit-wise, my units here are a. Or I can get things like meters times meter to give me meter square, or meters times meters times meters gives me meters cubed, okay? Or it could be bananas times bananas gives me banana square, or times bananas gives me bananas cubed. Okay, things of that nature. And I say bananas because we'll be talking about chemical compounds. the point of all this, if you set that up properly, you can convert anything from anything. And I have an example of an extreme conversion, very extreme. Let me show here. Okay. Now, many years ago, I used to teach at Carrington College, and then most of my students are either physical therapy students or dental hygiene students. So I gave this example to my dental hygiene students. I created arbitrarily some conversion factors. And I said, okay, 1 DH, which represents a dental hygiene student, is equal to 6 grapes. Then I said 3.5 grapes is equal to an orange, and 1 orange is equal to 6 toothbrushes, and 3 toothbrushes is equal to 1 banana. Very obscure examples. However, those are my conversion factors. Those could be factors in a chemical reaction. Instead of bananas, I could be talking about grams of carbon dioxide, okay? So then I posed the question, given the following conversion factors, how many DH students equal 4.5 bananas? Well, they were looking at me like I was from outer space, and I said, no, you can do it. You've got the conversion factors here. Just set up the problem properly, okay? Because we're given 4.5 bananas. So I need a conversion factor that will get rid of bananas and give me a different unit. And there it is, okay? Because I know from the conversion factor, which you, in this case, you can extrapolate and say from the chemical reaction, I know that there's a ratio of 3 to 1 of A over B. On this example here, we have a conversion factor of 3 toothbrushes to 1 banana. Okay, excuse my plural there. That's a misprint. So I set it up such that when I do the mathematics here, guess what? My bananas cancel out. Okay, so at this point, if I just do the math, unit-wise, I'm left with 2 brushes. But is that where I need to go? No, it's not, because I need to go all the way to dental hygiene students. So I need another factor that gets rid of 2 brushes and puts me into another unit. All right, so from that, I know that in 1 orange, there are 6 toothbrushes. So I set it up with 2 brushes in the denominator, okay? Leaving me with units of oranges on top. Okay, so now at the point I'm with oranges, I'm not still where I need to go, because where I need to go and keeping track of that, I need to know how many DH students, and never lose track of where I need to go, okay? So I need 1 more factor to get rid of the oranges, and I'm given 3.5 grapes per orange. Now I'm at the point where I'm at units of grape, and obviously I'm not there yet. I need 1 more factor, and yes, and the final factor is 1 DH student is equal to 6 grapes. So I look up my setup, I check it, making sure that things cancel out properly. My bananas cancel here, my toothbrushes cancel here, oranges cancel, okay? Grape cancels, and I'm done, because what I'm left with now are units of DH students, which could be units of, I don't know, grams of carbon dioxide for a chemical reaction. So now what's left, since I set that up properly, and notice I didn't invert the numbers, I left the numbers as is. I just put them either numerator or denominator, okay? Nor did I use the ratio system. Sometimes students want to use the ratio system, which is pretty good for maybe the first, maybe the second interaction. But if you're not keeping track properly, then that can throw you for a loop. So I highly recommend that you use this type of technique to set it up properly and follow it through, okay? One of the activities talks about setting up a conversion problem, which brings you to a point about the activities. Please read the instructions carefully. The instructions are very specific about what is needed in your upload, okay? So read them carefully. Okay, so now it's a matter of doing the math, okay? Plugging in the numbers in the calculator. All the conversion factors basically are there that I need. I end up with 1.3 DH students per 4.5 bananas. So this is an example of very extreme conversion factor with things that sound very crazy. But the point is, we're going to chemical reactions and they're going to look kind of crazy. You might get lost because you're like, whoa, where did I go? We're keeping track of units, always remembering what you're given. In this case, we're given 4.5 bananas, and then writing down at the end what you're looking for with respect to units will help you migrate through the problem, okay? Any questions about this crazy example? No? All right, well, let's go back to where we were. All right, so going to that, we know based on the table I gave you and so forth, that in 1 meter, there are 100 centimeters. C stands for century, 100 years a century. Therefore, there are 100 centimeters in 1 meter. The next one is 1 meter is equal to something decimeters, remembering that there are 10 years in a decade. Therefore, there are 10 decimeters in 1 meter. We got 1 kilometer, which means that it's 1,000 times greater. So there's 1,000 meters in 1 kilometer. Okay. And then the micrometer, there's a million micrometers in 1 meter. And then M for millennium, telling us it's 1,000 millimeters in 1 meter. Okay. So, it's good to know these. You can memorize them if you want, or use that little tool I gave you about century, decade, and so forth to help you with the prefixes. Okay. Now, this technique, that extreme technique, your book calls it factor label method. Okay. There's other names for it called dimensional analysis. I simply call it keep track of your units. Okay, to keep it simple. All right. So basically, they're telling you here, identify the units for what you want to find, what the answer is, what are you looking for, okay? And then identify what you're given in the problem. And then we start setting up conversion factors so we can get rid of the units of what we're given to eventually get to the units of what we're trying to find, okay? And then check the units after you set it up properly, make sure things cancel out properly, and then just do the math and report your answer, and obviously show your work. So if what we mean by showing your work is if you set up a problem of conversion, set them up like that extreme example I just gave you with the conversion factors, okay? All right, for example, here says how many, we're going to stay within the unit system here in the metric unit at this point. It says how many liters are in 2,389 milliliters, okay? So we write down what we're given, okay? And we're looking for liters, not forgetting what we're looking for with respect to units. And so I set up my first conversion factor because I know that in 1 liter, there are 1,000 milliliters, okay? And so now I can set it up and do the math, check my units, okay? Notice that millimeters cancel, therefore that tells me it's set up properly. So now it's a matter of taking 2,389 dividing by 1,000, all right? Which gives me 2.389, keeping your sig figs correct. Remember the conversion factor is a exact number, and therefore we're not playing a factor with respect to sig figs. All right. Second one here, they're asking you how many kilometers are in 12,300 centimeters. All right, so we write down what we're given, 12,300 centimeters. All right, so we need a conversion factor to get rid of centimeters. So I know that in 1 meter, there are 100 centimeters. So that gives me units of meters, but that's not where I need to go because my centimeters cancel right here, right here. So I need a second conversion factor that gets rid of my meters, leaving me the units of kilometers are what I'm looking for, okay? Now, you might be able to recognize that here that you can take those two conversion factors and create one, kilometers and centimeters. That's quite okay. You can do that. But until you're comfortable with that, keep them separated until you're comfortable about combining conversion factors, okay? So now it's a matter of note that you got 3 sig figs in your starting number, so my answer should contain 3 significant figures, okay? Because again, those conversion factors are exact numbers. All right, let me erase this, the other ones. There are some other factors here that you should hopefully know because you may need them. And like 2 cups in 1 pint, 2 pints in 1 quart, 4 quarts in a gallon. There's 1,760 yards per mile, or you can use 5,280 feet per yard, 3 feet per yard, or 36 inches per yard, so on and so forth. All right. Now, what I have a hard time with remembering is the cups and the pints and the quarts. So we got this little thing here to help out. I use it quite a bit. We got the big G here, big old G. Now notice within the big G, which represents a gallon, there are 4 Qs, which represent a quart. So therefore, there are 4 Qs or 4 quarts in 1 gallon. Now, if you look inside each quart, there are 2 Ps, which represent pints. Therefore, there are 2 pints per quart. And then further in, if you look inside the P, there are 2 Cs, which is cups, not cubic centimeters, but cups. There's 2 cups per pint, okay? 2 pints per quart, 4 quarts per gallon, okay? All of those can be set up here as a conversion factor, okay? 1 cup per pint, 1 pint per quart, 4 quarts per gallon. You got 3 conversion factors that can be written either cups on top, pints on the bottom, or vice versa. And the same is true for the other factors. All these conversion factors, treat them as a ratio that can be written 1 or 2 ways, depending on what you need. And for example, we have how many gallons are there in 44.5 cups, okay? And so we write down what we're given, cups. And so we get our first factor here, because I know that in 1 pint, there are 2 cups. So that will cancel my cups, leaving me pints with respect to units, which is not where I need to be because they're asking you how many gallons. So I need another factor, which gets rid of the pints, but gets me to quarts, okay? And so as I set up my system, okay, take a note, follow your units, make sure things are canceling out properly with respect to units, okay? And therefore, you know you have set that up properly. And so at this point, I'm at the units of quarts. I'm definitely not where I need to be, which is gallons. So I need 1 more factor, okay? Which we know that there's 4 quarts to the gallon, okay? I double check my units here. I make sure that I cancel out, okay? Now, let me ask you a quick question about these. I got 3 conversion factors, but can I combine them? Can somebody tell me how many? Let me clear it so you can see it a little better. How many cups in a gallon? You can unmute yourself and tell me. How many cups in a gallon? Okay, you got a chat. 16, that is correct. You're 16 because what you can do, what I meant by combining conversion factors, if I just take those 3 conversion factors right there, you can see that my pints cancel, my quarts cancel, okay, the way it's set up. And so I just multiply everything 2 times 2 times 4 gives me 16. So I end up with units of 1 gallon, there are 16 cups. Okay, so I have created a whole new conversion factor. And that's perfectly acceptable if you want to use that. But until such a time that you're comfortable with that, keep them separated, okay? This is a good example of a chemical reaction where you will have at least 3 conversion factors from going from A to B. Okay. Second question is asking how many inches in 3.5 yards? All right, so, oh yeah, let me give you the answer. The answer up there is 2.78 gallons in 44.5 cups, okay? 3 sig figs because the conversion factors are all exact numbers, so my answer should have 3 sig figs. How many inches in 3.5 yards? Okay, so we write down what we are given. That is our given 3.5 yards. Okay, so I got to get rid of yards, so I know that there are 3 feet in 1 yard. Okay, but I'm not at inches yet, so I need one more conversion factor. Okay, I need the 12-inch per foot, which after doing the math, I end up 126 inches. Now, let me double check my units. Okay, you can see my units all cancel out properly. Now, at this point, can I present this number 126 as a correct answer? With respect to sig figs. Okay. No, and that is correct. Rebecca, what will be my answer? What will be correct? Because what I'm asking is, how many sig figs do I need to have in my answer? 2, that's correct. Okay, 2 sig figs. 3 and 12 are all exact. So, but 126 has 3 sig figs. So what do I need to do? Okay, I got to go to my 2 sig fig position, which is the 2. Okay, look at the neighbor. We're going to do the rounding rule. See that the neighbor, which is 6, is greater than 5. Therefore, the 2 becomes 3. And then we put a 0 in place of the 6. Okay, we don't drop the 6 because we changed the magnitude. The magnitude we're in is in the hundreds. And if we were to drop that, that puts us into the tens. So our answer would be 130 inches. And that would be correct with respect to the significant figures. Okay. All right. I mentioned this already with respect to exact and approximate. That conversion factor 1 inch 2.54 centimeters and is an exact number, and therefore is not used with respect to determining significant figures, but the other 2 are. Okay. So they're given to you because you have them in the shapes table. So you definitely use that. In fact, when you're using conversion factors, again, I repeat, use these that we present to you. Also down the road, when we talk about the periodic table, in the periodic table, we have what are called atomic weights. Use atomic weights, the atomic weights in the periodic table. Again, if you use a different source, that will give you a different number of digits, which can affect your answer, okay? So stick with these and our periodic table. All right, so question now, we're going from metric to English. Here, they're asking you how many pounds are in 248 grams. This is an example of one of the activities. I want you to write out a conversion factor with at least 3 conversion units in there. Okay, so we know from the conversion factor that 1 pound is equal to 454 grams. And therefore, we could set it up with grams in the denominator and do the math. That conversion factor is not an exact number, so it could play a factor in sig figs. It has 3 sig figs, but the number we're given has 3 sig figs, so our answer should have 3 sig figs, which is 0.546 pounds. Okay, keeping track of your units. Notice that grams cancel out properly. Okay. Now, this example for activity wouldn't be an optimum example. Why? Because there's only one conversion factor. The activity requests that you have at least 3. So I would take the pounds and maybe convert them into something else, a different 2 more units. Here we go with how many inches are in 3.54 times 10 to the negative third kilometers. Okay, so you need your scientific notation, or you can write this out longhand, move the decimal point to the left by 3 positions, or you could input 3.54, use either the EXP or the double E button or the X10 to the X button on the calculator, and then type in the negative 3, put that in scientific notation. Okay, here we're going to use 3 conversion factors. Okay, and so we start off with kilometers. And we know that in 1 meter, 1 kilometer, there are 1,000 meters, okay? So that takes care of the kilometers, we got that out of the way, but it leaves us in units of meters. We're not where we need to be, okay? We need to go to inches. Now, I know that in 1 meter, there are 100 centimeters. So I plug in my second conversion factor, which will get rid of the meters, leaving me with centimeters. And now I'm still not at the units that I'm looking for because I want to end up with inches with respect to units. So I have 1 more conversion factor, and that is in 1 inch. There are 2.54 centimeters. Okay, follow my units. Centimeters are canceling, leaving me with units of inches. Therefore, I am where I'm supposed to be with respect to units. Now it's a matter of you calculating it and plugging your numbers in, and you should get 139 inches in 3.54 times 10 to the negative third kilometers. Sig figs are correct because all the conversion factors are exact numbers. Remember the 1 inch 2.54 is considered an exact number. We have 3 sig figs of the number we're given, so our answer should have 3 sig figs. Yeah. Any questions so far? Feel free to jump in, unmute yourself, and ask a question. And there's only 5 of us here, so well, 6 with me, so feel free to stop. All right, so now the question is, we have a 2-liter bottle, soda bottle. We need to figure out how many quarts are in 2 liters. Notice 2.0 liters, okay? So we got 2 sig figs to work with. All right, so we got liters. We want to get rid of liters, and we know that in 1 milliliter, in 1 liter, there are 1,000 milliliters, okay? And then from the conversion factors that are given on the shapes table, we have 1 quart is equal to 946 milliliters. Double checking my units. I can't overemphasize that. And it might sound like overkill, but yes, I want it to be overkill because when you get the chemical reactions, if you follow this format, you should not have a problem in doing your calculations. If you set the problem up, okay, correctly with respect to your units and following the units. So we do the math. 2.0, 2 sig figs. The 946 is not an exact number, but it has 3 sig figs. So our answer should not have more than 2 significant digits or significant figures, which is 2.1. Okay. That's the whole premise of significant figures, that you can plug that number in the calculator and you will get a bunch of numbers, but adding numbers to it you're making it more accurate than when you started off with, because you only have 2 sig figs to begin with. Your answer should not have more than 2 sig figs. Okay. All right. All right. So there's homework. Obviously, you all know there's worksheets in there. There's Dr. Kim's alternative videos. Go through them, get some examples. You know, these type of conversion factors are just something. Mathematics is, a lot of it's practice. You're just getting more practice as much as possible until you're comfortable with it. You'll find you'll be able to convert from one unit to the other with no problem once you get a lot of them under your belt and become comfortable with it. Okay. So I'm going to briefly talk about volume by displacement. This one's pretty straightforward. We all know when we jump in the tub, you know, when your tub is a certain level, that when you get in that tub, that level goes up, right? And if you had a way to measure the volume of your tub or your jacuzzi or whatever you're using, and you know the volume, and then you can immerse yourself in there and someone else measure the volume that goes up, that difference between where the volume ended up and the number and the volume that you started, that difference would represent your volume that you displace. That's what they're saying here. Okay. Remember that in 1 millimeter, it's equal to 1 cubic centimeter or 1 cc. So here they took a diamond, they placed it in a cylinder, graduated cylinder. It's just a cylinder with a scale so we can measure it, measure the volume. We put it in water and we started off at 20 milliliters of water. And then we threw the diamond in and it ended up at 34.7 milliliters. So the question is, what is the volume of the diamond? Now the volume of the diamond is not 34.7 milliliters, okay? The volume of the diamond is the difference between where it ended and where it started. That is the actual volume of the diamond. Remember this if you do the extra credit. The extra credit that is given to you deals with immersing objects. And remember that you're looking at the object you immerse, not the total volume that you start off with, okay? And keep that in the back of your head if you do that extra credit. So this thing now has a volume of 14.7. Now, this is good. This is one technique that is used a lot for objects that we cannot directly measure, because we know that if you measure length, width, and height, if you have an object like a box, you just measure length, width, and height, you got the volume. But objects that are not that rectangular, easy to measure, the only really good way to do it is by displacement, okay? So, yeah, we know that diamonds are carbon is solid. Now, how do we calculate the volume of a rectangle? All right, we know that volume is 3 dimensions, length, width, and height, okay? And so to calculate the volume of a box, in this case a shoe box, it measures 24 by 11 by 16. We simply measure, do the math, okay? And we end up with the units of cubic centimeters, right? Because centimeters times centimeters equals centimeters squared times centimeters equals centimeters cubed. And doing the math, we end up with 4,200 cubic centimeters or 4,200 milliliters, okay? Because we know that 1 cubic centimeter is equal to 1 milliliter. Now, with this manner of calculating the volume, either directly or by displacement, we can now do things like density. Density is a ratio. Here we go, another ratio again. It is a ratio of mass over volume, okay? All matter has density. All of us has density. Anything around us has density. If you can measure, you can take your weight, get your mass, and if you had that jacuzzi to figure out the volume of this place, guess what? You can calculate your density of your body, okay? So the units utilized normally are the middle units, where you have grams per milliliter, but you can also see them as grams per cubic centimeter or grams per cc, okay? But the standard units are normally grams per milliliter, okay? And density is just a matter of thinking about how much matter is in a given space. All right, so with that being said, which state of matter is the most dense? Well, obviously the solid, okay? And the least dense would be the gas. Very, very low density, very small numbers. Water is our kind of our benchmark, reference point, where water under room temperature is normally 1 gram per cubic centimeter or 1 gram per milliliter. Now, in general, anything with a density greater than 1, if you were to put it in water, it would sink. And anything with a density less than 1, it will float, okay? And that's what happens to ice. You would think that ice just being water, that it would just sink or just stay the same, but it does float, because what happens to ice water is if I take a gram of water and I measure it, it has 1 volume, the same volume. One gram of water has a volume of 1 milliliter. So 1 divided by 1 is 1 gram per cubic centimeter or 1 milliliter. Now, when I take that same gram of ice and I freeze it, what happens in the process of changing its physical state, its volume actually increases. So instead of having a volume of 1 milliliter, it may have a volume now of 1.1. So if you take 1 gram, because that's how much you started off with, and now you divide it by 1.1, guess what? You get a number less than 1. It's about 0.9. So the density of ice is about 0.9. So in water, ice being less than 1 will float, okay? Simply because the volume changed. Now, let me ask you a question with respect to density. Now, we all heard the old question. Which weighs more, a ton of bricks or a ton of feathers? Well, obviously they both weigh the same, right? Because it's a ton of each. Now, let me ask you the question. Which would have the greater density? A loaf of bread, or that same loaf of bread squished down? You know how bread you can take and squish it down? Who would have the greater density? A regular loaf of bread that you buy at the grocery store, okay? Or another same brand of loaf of bread, but this time you take it, you know how kids do sometimes, they take your bread and they squish it down, okay? They're both a loaf of bread, approximately have the same weight. Would they have the same density, or would they be different? Okay. Small bread, that's correct. Small bread will be more dense. They both have the same mass, okay? Just take 2 identical loaves of bread. And I can take that loaf of bread and I can measure its volume, length, width, and height, and I have a density, correct? I take another loaf of bread of the same weight. This time I squish it. What have I done? I have changed the volume, length, width, and height, which means in the denominator, I change the number, okay? A smaller volume. So I'm dividing now by a smaller number, and guess what? That ratio goes up, okay? Yeah, so keep that in mind too when we talk about density and, you know, when we talk about density in the homework or in the quizzes. Now, let me ask you another question about density. I got a Hershey bar, okay? And I can measure the length, width, and height. I can weigh it, I get a density. But I take off a little piece, okay, that little piece. Does that little piece have the same density as the original piece? Or is it different? Be the same, exactly, because I haven't changed anything. I took a little piece, I have a different weight now, and I have a different volume, but that ratio is going to be the same. The ratio of 10 over 2 is the same as 5/1, is it not? Okay. All I've done is decrease the mass and also decrease the volume, but that ratio remains the same. All right, good. All right, so calculating density, pretty straightforward. You got the mass, you got the volume, do the math, there it is. But we also can use density to calculate mass or volume, okay? Because the density that we're given is a ratio. And so, for example, the density of chloroform. Chloroform is a chemical they used to use back in the day when they wanted to knock you out during surgery, you know. Put in the mask and you're out like a light. They use other stuff now. But anyway, chloroform has a density of 1.48 grams per milliliter, okay? Think about that ratio. That means that if I measure out 1 milliliter, it has a weight of 1.48 grams, okay? That's all density is telling you. Its volume, its weight per given volume. All right, so therefore, being a ratio, like we've been talking about earlier, I can write it one or two ways, with grams in the numerator or grams in the denominator. Which one I use depends on the question and what the units are that I'm looking for. If I'm looking for grams, then I write it as given on the left. If I'm given volume, milliliters. If I'm looking for volume and given grams, then I use the one on the right, okay? So you got to look at the question carefully. This example is basically a straightforward, what is the density? There's a necklace, weighs 484.56 grams, and they already calculated the volume of 25.64 milliliters. It's a simple matter of plugging in the numbers and you calculate its density. Okay, keeping track of your sig figs. In both cases, the weight and the volume are not exact numbers, but we are dividing by 4 sig figs in the denominator. Therefore, our answer should have no more than 4 sig figs. So the density of that necklace is 18.90 grams per milliliter. Okay, so direct calculation of density is just follow the equation. Divide your mass by volume. Now, sometimes you're given the density of a chemical, in this case chloroform, and they're asking you, let me highlight that. They're asking you how many grams, okay, would 17.5 milliliters of chloroform mass. So if you measured out 17.5 volume-wise chloroform, what is its weight? Okay, given the density of chloroform is 1.48 grams per milliliter. So that means since I'm looking for grams and I have milliliters, I'm going to write it just the density just as is. Okay, because when I do the math, check my units, my milliliters cancel. And so now I can actually get a weight of 25.9 grams. Now, the mistake that happens a lot with this type of calculation is the students forget the units and they report the units as 25.9 grams per milliliter. But that's not correct because you are multiplying, you check your units. You can see the milliliters cancel out. So the only units you should have at the end are grams. Furthermore, the question is asking you how many grams, how much does it weigh? So that should tell you again that the only units you should have at the end are grams, okay? All right, so that's an example, a straightforward example of given volume and the density, you can calculate the grams. So you can invert this too, because what this says is that if I weigh out 25.9 grams of chloroform, which you can, it would have a volume of 17.5 milliliters at 25 degrees. So you can utilize this one or two ways. You know how many milliliters, you know how many grams, okay? So if I take 25.9 grams and divide it by 17.5, guess what? I end up with 1.48 grams per milliliters, which is the density of chloroform. All right, let me go on to the next one. Now, in this case, the question being asked, and again, it's important to read the question carefully. They're asking you, how many milliliters? Okay, so that's what we're looking for unit-wise. Would 0.0735 grams of chloroform occupy? So if I weigh out 0.735 grams of chloroform on a balance, what is the volume that it occupies? What is its volume? Okay, so this time we're taking the density and we're going to set it up with milliliters in the numerator, grams in the denominator. Okay, why? Because we're looking for milliliters. That is what the problem is asking us for. So we write down what we're given, and now we invert the density, leave the numbers as given. Okay, verify that you set that up properly by follow the units. Notice that my grams cancel out, and that tells you, okay, I set it up properly. Okay, do the math. You can track your sig figs. All right, so 0.0497 milliliters would weigh 0.0735 grams. Okay. All right, let me clear this up here a little bit. Now, so much for this. We're going to talk about temperature a little bit and energy. Again, this is pretty self-explanatory. I'm hoping that you know that hot molecules, when you heat something up, they're going to move fast. They are. You boil water, those molecules of water are going to be bumping up pretty hard against each other. Eventually, they're going to go into the atmosphere, and they're going to be moving. Why? Because they have a lot of energy. They are high on energy. Okay, energy put into the system. Now, if I wanted to slow them down a little bit, what do? I take the energy away from it, bring in a little bit of cold, and that's going to slow them down. When they start slowing down, the molecules start interacting with each other a little bit more, and then eventually they will condense. If we're talking about steam or even clouds and so forth, they will condense into liquid because they've lost their energy. Okay. The thing about energy, and the thing about energy in nature, it always goes from a state of high energy to low energy. Okay, that's important. Now, yes, we can make it go from low to high, but we got to put energy into the system. The case in point is your freezer, your refrigerator. It doesn't spontaneously get cold. We're putting energy into the system to drop the temperature of your refrigerator. Okay. Now, let's take, for example, you're in the shower, nice hot shower in the morning. Okay. It's winter time. And so you step out of the shower. So what happens? It gets cold, right? Now, you're in the hot shower. You're in the state of high energy because the hot shower. You step into the cold room. The energy now transfers from you, because you're the one with the high energy, to the room. So in effect, you lose energy, and therefore you get cold outside the shower. Okay, so your temperature drops. You decide, let me jump back into the shower. You jump back into the shower and you warm up. Now, why do you warm up? Because the environment of the shower is a lot higher than you, because you were outside, your temperature dropped. So now the transfer energy goes from the room of the shower to you, and you warm up. Okay. Eventually, high and low, they equate, and they get to room temperature, whatever temperature you're at. Get a hot cup of coffee, you leave it on your kitchen top. You come back an hour later, it's cold, because it lost that energy to the environment and it got cold. Now, if you were in the North Pole and you had a hot cup of coffee and you let it there outside someplace, You come back in an hour or so, it's frozen because the environment that you're in is a much colder temperature, okay? Now, temperature, we measure that with the thermometer. The thermometer does not measure energy, okay? It measures the result of putting energy into the system or taking energy out. So just a scale, that's all it is. And we have 3 scales we work with. Obviously, we're all familiar with the Fahrenheit, that's the English scale. But in science, the metric scale is Celsius. And then we have another one in science, which we call Kelvin. Now, the thing about these first 2 scales is going up in temperature or going down in temperature, they go to an infinite value. So Celsius can go to infinity in the plus side, so does Fahrenheit, or they both can go to infinity going to the negative side. Kelvin does not. Kelvin stops at 0, okay? That is what we call absolute 0. That is where all matter stops moving. Even as we've gotten close to that temperature, but not quite. And an interesting side note about that, that the atoms and matter tends to, there's some strange things going on down there at that low temperature that they're still investigating. Okay, so we've made some marks there for you. We know that water boils in Fahrenheit 212, in Celsius 100 degrees. The freezing point of water in Fahrenheit is 32, in Celsius is 0. That's why I like the Celsius scale. Very straightforward. 0 freezes, 100 is boiling. Okay. To get to Kelvin, we have to go through Celsius. And what we do is we add the number 273 to your Celsius scale to get to Kelvin. So if we start with Fahrenheit and we need to get to Kelvin, we first have to convert to Celsius from Fahrenheit and then add the 273 to get to Kelvin. You can't go directly. There's no conversion factor that takes you directly from Fahrenheit to Kelvin. You have to go through Celsius. All right, so the conversion table, it's given to you. It's in the shapes table. It's not necessary to memorize anything. It's there, okay? You just plug and play, all right? So you have Fahrenheit. You want to go to Celsius, take Fahrenheit, subtract 32 and divide it by 1.8. It gives you the degrees in Celsius. If you have Celsius, you want to go to Fahrenheit, take Celsius, multiply by 1.8, and add 32, that gives you Fahrenheit. Kelvin, you need Celsius and add 273. And so this particular problem, they say Phoenix can get to be 115 degrees Fahrenheit, okay? What is it in Celsius? And what is it in Kelvin? Practice inputting that number. You should end up with 46 in Celsius and 319 in Kelvin. If you don't, let me know. Shoot me an email and we'll talk you through it. Maybe you pushed in the wrong number or something, okay? All right. So going back to energy, we got 2 beakers here. It's kind of a silly question because they're asking you which of these 2 beakers has a higher temperature? Well, they're both listed at 100 degrees Fahrenheit. So they both have the same temperature. And then they're asking you which has the greater amount of heat. Okay, now it's a little bit different. Okay, well, A has the greater amount of heat. Think about this. You got a small pot of water boiling, and you got a big pot over here to make spaghetti, big old tall pot of water boiling. Now, if you want one of these to spill on you, which would you pick? The little small pot or that big old pot of spaghetti? Obviously, the little pot. They're both boiling of water, they're both boiling. And so, but the little pot has less molecules of water, therefore they have less amount of heat. Okay, because of the volume. All right, so I would take the smaller cup. Now that has a big factor because out in the Pacific, there's a body of water called El Nino that really has an effect. And it's only a 1 or 2 degree difference with respect to temperature of the rest of the ocean. But the body's so large that that amount of energy has a big effect on the world environment. And La Nina is another body of water out there, but it's much smaller as far as the amount. And that also has effect on the weather. So anyway, let's talk about briefly about heat transfer. Okay, like I mentioned, heat transfers from high to low. Okay, not cold to hot, high to low. And so you got a cookie, take it out of the oven. Who's losing the heat? Obviously the cookie, right? And you grab it, with your hand. Who's gaining the heat? Your hand. You might gain 2 heat because it can burn you. Okay, because you are lower energy than that cookie coming out of the oven. So that heat transfer goes from the cookie to your hand. Okay. All right, so same scenario, similar scenario, you take a piece of metal, put it in the freezer, and then you put it in a bucket of water. Okay, does the temperature of the metal increase, decrease, or remain the same? So you got a cold, 0 degrees chunk of metal, you stick it in the boiling water. Obviously, the metal temperature is going to go up, and guess what? Because it's absorbing the heat from the water, and that temperature goes down. Okay, and so eventually that temperature will stabilize at some point, depending on what environment it's in. So if coffee's too hot, throw in a spoon. Okay, that cools things out pretty quick. All right, so always remember, energy transfers from high to low. So, not the quiz, but the exam obviously is coming up. So today and tomorrow. So review the chapters, look at the sheets, not only the YouTube videos on the website, but the ones I'm going to load up. I always load these up. I mark them SCC. But you can go in there, you feel free, because I mark what chapters, feel free to view the other ones from GCC, where we go over the same topic, except because this class only meets once a week, we tend to be about 1 chapter behind. The other ones, we're already up to chapter 4, but we only meet here once a week. So any, know your say figs, okay? And don't forget the assignments that need to be due. Someone asked me about the assignments, the ones that people haven't done them. How can I say this? The assignments are, except the exams, are always open. Okay. The assignments are always open. However, they all have due dates, and so even though you do it late, you can still go do the assignments late, but there is a penalty for doing the exam late. Okay, we talked about that before. So in fact, they still open. All assignments except the exams stay open until about, I believe, the 18th. Okay, but don't wait that long to do all your assignments. Because you're not going to get all the points for one thing. Okay. All right. Any questions? Comments? Because basically, I went over chapter 3, which is what our first exam is about, chapters 1 to 3. And what time is it? 2:16. What I like to do is just take a quick 5-minute break. Okay, I got to check on something. And then if there's not any questions, I'm going to jump into chapter 4. Okay, so, all right, so. Well, I'll be back in a little bit. Okay, I'm back. All right. Can you guys hear me okay? I've been having some challenges with my electronics, so yeah, okay, good.
I can hear you.
All right. Okay, great. Thank you. I will proceed with chapter 7, because now we get back to chemistry. All right. So, excuse me, 4. What did I say, 7? All right. Here we're going to start talking about the atoms. Okay, we're going to start off with atoms. I'm going to describe that a little bit, and our model, our current model of an atom. And then eventually we're going to progress into taking the atoms to make compounds. And then eventually we're going to take these compounds to react with other compounds and start talking about chemical reactions and the different types of chemical reactions and be able to predict products and so forth. But first, like, you know, chemistry sometimes is a language. We got to start with the language, and we're going to start with the alphabet first before we start building words. Okay. Now, back in the 1800s, excuse me, 1800s, scientist by the name of Dalton proposed the idea that the atoms were indestructible particles, which he called atoms. The word atoms is not a new concept. That concept goes even further back to the Greeks. So anyway, he proposed that matter was made up, or the elements were made up of atoms, and they were indestructible. But it turns out that's not the case, because we find out that these atoms are actually made up of particles, subatomic particles. Now, we're going to be talking about just 3 of the particles. So we're going to be talking about protons, neutrons, and electrons. And the thing that got me excited about chemistry 100 years ago was these crazy electrons, because that's where all the action is. That's where all the chemical reactions occur, is the electrons. And these are the same electrons or similar electrons that occur that are being used right now as we do this discussion. Some of you are working on the battery, on your electronics, running out the battery. Those are electrons that are powering your electronic device. You walk on carpet and you touch something and you get zapped. Those are electrons. Or you have a bad hair day and you wake up with your hair just doing this poof. You know, those are electrons interacting with each other. And they're all around us. They're all around us, and they have such a big impact on how chemicals react, and they're so tiny, okay? So very tiny, but more on that later on. So he also proposed that all atoms of an element are identical and have the same properties. Well, that didn't turn out so quite true also, because, for example, diamonds. Diamonds are made up of carbon atoms, okay? But you can take something like what is called a graphite, which is also made of carbon. And graphite, if you don't know what it is, it's a dry lubricant. It's very slimy. Diamonds are the hardest thing on earth to date, okay? And they're also made of carbon, pure diamonds. But yet, both being made of carbon and totally different properties. And that's because the way in the diamond structure, they're put together differently than the ones in the graphite, but they're still carbon. So this thought was also not 100% true, okay? Now, he also proposed that which this part is true, then when different elements combine, they form compounds. So this little example, we got 2 kind of gold-looking spheres, or diatomic, with 2 red ones, also diatomic. They come together and they make 2 compounds. Okay, compounds, because there's that compound by definition is a chunk of matter which has 2 or more different atoms combined. And here you see a red and a gold combined to make a compound. Okay. Also note that based on the conservation of matter, we start off with 2 red ones, and guess what? We end up with 2 red ones. They may be in different form, but it's still the same element. The same is true for the gold ones. 2 gold ones to begin with, we end up with 2 gold ones at the end, but in different format. Classic example would be something that you ingest that contains carbon. That carbon, as you metabolize it, will eventually maybe come out, it could be in the form of, say, a leaf, a salad, or chunk of meat, that particular carbon atom. As you metabolize it and convert it to some byproduct, it could be converted to carbon dioxide, which you inhale. It's the same carbon that went in, and it's the same carbon as it went out. It's just in a different form, okay? His other contribution was when atoms came together to form a compound, they come together in whole ratios. And this is a true statement, because, for example, we write down H2O. Well, that subscript tells us how many atoms of hydrogen are involved with oxygen. Okay, so there are 2 whole atoms of hydrogen per one. There's no subscript 1 for oxygen. It's understood, like in mathematics, no number means it's understood to be 1. That there's 1 atom of oxygen combined to 2 atoms of hydrogen. Now, it doesn't tell us how they're combined, but which brings me to a point. You will always be told, normally what happens is we have a central atom, which is the main atom, and anything that's combined to it is combined around it. And you'll always be told who is the central atom. So there won't be any guessing. 9 times out of 10, when it's written down, normally, with the exception of H2O, normally the first atom written down in the formula is the central atom, and then everything else that follows is bonded to the central atom. Okay, but they come together in small whole ratios. That subscript, once it's set, we don't change it, because there is a law, which we'll talk about, that's the ratio that they come together to form that particular compound. Okay, if we need to add, for whatever reason, more, we put a coefficient in front of H2O. So we will put a 2 in front of H2O to say, hey, we have 2 molecules of water, or 3, or 4. We can change that coefficient all we want. But the subscripts, we leave alone. That is the ratio of those atoms that combine. Okay? Now, they can combine to form different compounds. They always don't come together 2 to 1, 1 to 1. They vary. An example here would be CO, capital C, capital O, okay, which represents carbon monoxide, okay? The other example, which we're all familiar with also, is carbon dioxide. Notice the name I gave it, carbon, 2 oxygens, dioxide. Carbon, 1 oxygen, monoxide. In this case, the way it's written, carbon is the central atom, okay? And when you only have 1 of each, there's really no central atom, like the example in the left. But when you have more than 1 atom, like carbon dioxide, the red sphere represents the carbon, and then the gray represents the 2 oxygens that are bonded around carbon, okay? Now, I'm going to see this link kind of acts up a little bit, but I'm going to see if we can hear it. I'm going to put the closed captions because the sound was kind of sketchy. I don't know if it's my connection or the website's connection, but anyway, 1800s, we started with Dalton, and we move along. We're getting close to 1900s. So in 1897, a scientist by the name of J.J. Thomson, he is credited with discovery of the electron. Okay, he used what's called a cathode ray tube. This is really the precursor to the old-fashioned television. I don't know if you've ever seen one of those. Now with the LED TVs, they're all flat screen, but maybe your grandparents have one. I still have the old-fashioned TV with a big old end and very heavy. This was the precursor. What happens is that he had what's called a cathode ray tube, which generates some particles. That's not important to what type of particles right now, but he was able to project his particles on the screen, which these particles that have high energy are absorbed by the particles on the screen and excite the particles on the screen. And like I said earlier, nature absorbs that energy, but it doesn't like to hang out there in the we call that the excited state. Nature wants to stay in the ground state, the stable state. We can push it up for a little bit, but it comes back down. And when those particles hit the surface of the screen, they excited the molecules of the screen, and then when it came back down to the ground state, they emitted that energy, conservation of energy, whatever energy goes in, same amount must go out. In this case, it went out as light, and there he was able to see this little flash, okay? And so let's see if we can see the audio on this. All right, so, come on. Okay. It probably sounds like the sound is going in and out, but basically here's the tube on the far left, and it's creating these particles that are being shot through the screen up front. These particles are in high excited state. They hit the surface, it has this material coated on them. They excite those molecules. Those molecules go back to the ground state and then emit the energy they absorb as light. So they see this little green particle or green light on the screen. You know, like I said, this is the beginning of the old-fashioned television. That's what you were looking at, is the excitement of molecules. In fact, the screen you're looking at now is similar. All the screen that we're looking at molecules being excited, but very fast, so to give us this image that we're all seeing right now as we speak. Now here's the part that he was kind of surprised, because he put in a couple plates here with the charge, positive side and negative charge. And lo and behold, that beam shifted, okay, which suggested that that beam must be charged, okay, because it's being attracted to the positive side. And that's why those old TVs were so heavy, because in the back, they had magnets in the back that localized and made that scanning screen go up and refreshed it so you could see an image on the old-fashioned televisions. Okay. Because those particles were charged based on the plates that he put in earlier, any charged particle also has associated with it a magnetic component, okay? Which, for example, a motor has the same thing. A motor is nothing more than a current running through there. And in there we have magnetic component there will drive whatever is going to drive. The same is true with a generator. We can move the magnet to create electricity. And so here we shows here that definitely a charged particle, because as you put that magnet, it caused the magnetic component of that beam to pull away, okay? Okay. You're not going to be responsible for that crazy equation there. That's not the point of this. The point of this, he was able to calculate that ratio. Okay. And being able to calculate that ratio, that means there's two variables in that ratio. Further down the road, other scientists are able to calculate some of those another variable, and was able from that ratio be able to calculate the mass of the electron. And that's why we're able to get a relative weight of the electron. And it turns out they're extremely, extremely tiny. So J.J. Thomson, based on this type of work here, who, like I said, this is the precursor for the old-fashioned television, is attributed to the discovery of the electron. Okay, so with that information, he came about with his model of the atom, and that was what's called the plum pudding model. He proposed that somewhere in the atom was a positive component, okay, and that the electrons were kind of just scattered all around arbitrarily. Okay, so that was his model, plum pudding. And so for a while, that pretty much held true. But with science, anytime there's a new stuff coming up, our model changes. Even the model we have today could change next week. But currently, the model that we're going to eventually talk about is the model that we have until such time the model gets changed. Well, we're talking about 1904. Bear in mind here that during this time period, 1900 to about the 1930s, there was a lot of work that was found and discovered. This is the time period of Einstein, but there was other scientists, that were just as I would say smart as Einstein, J.J. Thomson, for example, and some other ones that come up. But Einstein had the better PR representative. Now, he's the one that noted most in these. So here we go. We just said 1904. A few years later, another scientist by the name of Rutherford, British scientist, he kind of took a little bit of the work that J.J. did as far as equipment and did something a little bit different, and was quite surprised. What he did was basically create some other particles, what we call alpha particles. Anyway, they're not important that we know we're going to talk about those, but these particles that he shot them through a gold foil, okay? Now, he had proposed that if the plum pudding model was correct, and he also used this fluorescent material, as JJ did, that these particles would just shoot right through the gold foil and illuminate the material up front. It turns out that what was happening is some of these particles are being ricocheted in different angles, just like shooting pool and you're trying to shoot an angle shot to the corner pocket. Instead of going straight through, you kind of have to angle it to get that cue ball to get to the corner pocket. That was what was happening. So let's take a look at that video and see. We can see it here. Come on. Let me check something. Hold on one second. Okay. Well, basically in that scenario, the alpha particles did not go through completely, but they were being scattered. And so evidently the alpha particles, which are pretty small, were hitting something pretty big enough to scatter them. And so what Rutherford proposed, that the atom must consist of a very heavy, dense nucleus, okay? And so the model to the left represents Thomson's plumbing model, okay? And the one is to the right is Rutherford's, which is the current model that we have, that in the nucleus, we have the proton, the existence of a proton. So that is what Rutherford is credited to discover, was the proton / nucleus, okay? Later on, scientists by the name of Chadwick is discovered the neutron. And so Rutherford has a proton / nucleus, and then Chadwick comes along and he actually finds the neutron. And so that's our model that you see depicted here with respect and that picture, where you have in the center a very dense nucleus, which the proton exists, and the neutron. And in some place somewhere are the electrons that J.J. Thomson had demonstrated exist. Now, the next chapter, we're going to get in more detail about how the electrons are really put together with respect to our model, because they're not just haphazardly just placed up there. We'll find out that there are very specific levels, okay? And so the other thing is that the atom is basically a lot of empty space. It's amazing. If I were to scale up hydrogen atom and I represented the nucleus, my electron, because hydrogen has one electron, at my scale now, my electron will be roughly about 3/4 of a mile away. Quite a distance away. However, that interaction between the two is just the force that keeps me there is strong. There's forces in nature that we don't quite understand, and what's going on, we're still working on it. And even our own solar system, we have Halley's Comet that comes around every 76 years, and it goes away so far, but it works its way back from the sun eventually. And it's the distance, you would think, or that distance of travel, that it wouldn't be attractive to come back. But something's going on to make it come back. So there's a lot of forces going on. Another scale to help you out with respect to the atom, again, if the nucleus is the size of a small marble, then the whole atom will be about the size of the Cardinal Stadium. So that's pretty big, fairly big. So what we have here with respect to the subatomic particles, the electron, the proton, the neutron, they all have their little symbol. The electron is denoted by the lowercase e, and it has a superscript minus because it has a negative charge. The proton, superscript positive, because it has a positive charge. And the little n, lowercase n, for the neutron, because it has a 0 charge, no charge on it. Now, we have, because the weights on these things, the masses in them are pretty small, we introduced what's called the relative mass. Okay, so both the proton and neutron have been assigned a value, a relative mass of 1. Now, what does that mean? Well, let's say me, I'm approximately 200 pounds. And so someone else that weighs maybe 400 pounds, well, their relative mass would be a 2 because they're twice my weight. So my relative weight would be 1, their relative weight would be 2. And that's what they've done here. Now, with respect to the electron is extremely tiny. It's roughly 1 in 1,000, almost 2,000 as far as weight, relative weight. To give you an idea, if something weighed 1,836 pounds, for example, or kilograms, then the electron will weigh about 1 kilogram. So there's some quite disparity in weight when we compare it to the proton and the neutron. So what we essentially say that the mass of the electron is approximately 0. It's not 0, but it's so small that we just treat it as 0. That property that comes into play later on next semester is because it is so small, it actually has light properties, wave-like properties, and we're going to tie into that next chapter. Okay, so they're very, very small, and yet so small they have such an impact. As I mentioned, chemical reactions is all about, chemistry is all about breaking and making bonds which entail the electrons. Okay. Now, let's talk briefly about the atomic notation. There's a format by convention and how we depict an element. There's 118 elements. Now, if you haven't done so, I would make sure you download that periodic table, because I'm going to refer to it quite a bit. We use it quite a bit to give us all kinds of information. It looks like a bunch of columns and rows and some Roman numerals up there, but trust me, that periodic table can answer a lot of questions very quickly, okay, just by the position of the atom, the element, and where it's at. So how do we depict that? Well, SY represents a symbol. We briefly talked about that. It's either going to be a uppercase one letter or a uppercase one letter and lowercase second letter, okay? Now, superscript left denotes what is called the mass number, okay? The mass number is a whole number, not to be confused with the atomic weight. If you look at the periodic table, you'll see underneath the symbol, you have a decimal number, okay? That is the atomic weight. That is not a whole number, okay? So that is not the mass number. The mass number is the sum of the protons and the neutrons. And remember, the relative AMU, the atomic mass unit, is 1. So the mass number will always have a whole number. Now, the atomic number is given to you by subscript left here, denoted here by Z, and that's on the periodic table. If you look at the periodic table, there's 118 atomic numbers there. That represents that particular element, okay? Now, the atomic number is equal to the number of protons and electrons that element has, okay? And so let me show you here real quick. Go ahead, where did my, there it is. Okay, so if we look at the periodic table, and if we take a carbon, for example, which is number 6, now like I said, you really need to be familiar with at least the first 20 elements, and then about half a dozen different ones here to begin with. We're eventually going to hit a lot of these, but not all 118. So here we got carbon, denoted by the letter C. Its atomic number is 6, which tells you there are 6 protons and 6 electrons, okay? Now, you can pick any element. If you look at sodium over here, sodium is number 11, which tells you there's 11 protons and 11 electrons. Now, the protons I just stated have a positive charge, and the electrons have a negative charge. So if I have 11 positives and 11 negatives, mathematically, what is my net charge? Wouldn't that be 0? Yeah. We will eventually talk about how some of these guys lose electrons and gain electrons. Remember, the proton defines what the element is. The moment I change the number of protons, I've created a whole new element. For carbon number 6, if I lose a proton, I become boron number 5, okay? So the proton defines the element. And it's difficult to get rid of a proton. It's not that easy. Why? Because it's in the center nucleus. It takes a lot of energy to knock one out. Can it happen? Sure it can. And the result will be something like a nuclear reaction. Okay, not too good. All right, so there's a lot of energy in there. So But I also stated that the electrons and the neutrons, you can lose and gain those all day long. I can lose electrons or I can gain electrons. I can lose neutrons or gain neutrons, but I don't change what that element is, okay? That's important, okay? I do not change that element. So I can look at any of, you can pick out any of these elements, and knowing its atomic number, you know how many protons and how many electrons. Now, how do we know how many neutrons we have? Well, I'll show you something what we do. What you do is you take the atomic weight and you round it up to the nearest whole number, okay? And remember, the atomic weight is that decimal number underneath the symbol on the periodic table. So if you take 12.01, round it up to the nearest whole number, it becomes 12. That is the mass number, okay? And if we subtract the number of protons, guess what we have? The number of neutrons. Because the mass number is the sum of the protons and the neutrons in whole numbers. All right, so carbon has 6 protons, 6 electrons, and 6 neutrons, okay? Now that number 12.01 is an average of what we call the isotopes of all carbon. Now, what do I mean by isotopes? The next chapters we'll talk about that more. But what happens, some of these elements carry more neutrons than the other, okay? So we all heard about carbon 12, carbon, someplace maybe you haven't, carbon 13, carbon 14 datings, things like that. Those are carbon. The only difference between carbon 13, carbon 14 is from carbon 12 is the number of neutrons, okay? Now, the reason we can round that number up to the nearest whole number is because these carbons, isotopes, exist in different percentages. And the most abundant, the most common isotope for carbon is carbon 12. And what is done is they take the average of all the mass numbers for all the isotopes, carbon 11, carbon 12, carbon 13, carbon 14, and then we incorporate the percentage that they are out there in nature, and we take the average. We take the average of all those numbers, and that average gives us 12.01. Okay, that is why we don't use the atomic weights in calculating sig figs, because that number 12.01 is the average of whole numbers, okay? And therefore, having an average of whole numbers, they have an infinite number of significant figures. So because that, we treat them as exact numbers. So they don't play a factor in sig figs. All right, so going to sodium, can anybody tell me how many neutrons sodium has for the most common isotope, which is carbon and sodium 23? How many neutrons was I circled sodium on the periodic table? We know it has 11 protons and 11 electrons. How many neutrons does it have? Take a wild guess. Well, not so wild. It's an educated guess here. Based on what I just told you what to do with the atomic weight. Atomic weight is 22.99. Rounded up to the nearest whole number. What would that number be? Let me see. 23. That's correct, Claire. Now take that 23 and subtract 11. 12. Okay. That tells you that sodium 23, okay, has 11 protons 11 electrons, and 12 neutrons. 12 neutrons. Okay. But getting close to that time, but what I want to do is I want to we continue here, I want to give me a second here. I want to direct you back to the, let me clear all this out. To give you a better idea about, oh, I got to log back in. Going back to the course website, I put in the modules, let me share here, the course website. Okay, I hope you all can see that. Okay, as you come into your class, okay, that's my home page. But on the far left here, you got modules. Click the modules, okay? And a variety of different modules. You got the welcome, first steps, and broken up all the chapters, what we talked about before. And you go all the way down to the last one where it says additional resources, okay? Now there you have a periodic table, which is an interactive periodic table that gives you information about all the elements. There's nice little videos with some crazy looking scientists talking about the elements. It's a good thing to look at if you like. But there's one called Build an Atom. If you click on that, it sends you to a simulation and click on the atom choice, okay? Now here you have a simulation of an atom, and you have a bucket of protons, neutrons, and electrons. Now notice if I grab a proton and bring it close by, guess where it goes? Nope, it went back to the bucket. Bring it in close, maybe the inner dotted line. Oh, I went to the center, right? Because that's where protons exist. But look what I created. I created hydrogen. If I had another proton, I'd create helium, okay? So on and so forth. So I'm going to take one out. Now, if I take an electron, grab an electron and put it on the outermost line, dotted line here, guess where it goes? It goes in the inner line. That dotted line, we're going to have more in this in the next chapter, represents the different energy levels that electrons exist. And so you notice when I grabbed it and I left it in the outermost line, well, that's not the most stable position, so it's going to go into the inner stable position. Here, there's two energy levels denoted by the dotted lines, okay? And so I have a net charge. If I take my electron out, look at my net charge. It's a +1, right? Because the proton is a +1. The moment I put the electron back in, my net charge is 0, okay? And if I add another electron, look at my net charge, because now I have an extra electron, my net charge is a -1, okay? So gaining electrons above what you have makes the element a negative charge species, and removing an electron makes it a positive charge species, okay? Now, at this moment, I can grab a neutron and I put it in the center, that's where it goes, okay? And I can show here that hydrogen with one neutron is fairly stable. Hydrogen normally does not have the most common isotope of hydrogen does not have a neutron. If you look at the periodic table, hydrogen has atomic number 1 and a mass number of 1. 1 minus 1 is 0. So the isotope that is most common is that hydrogen right there. Now, hydrogen does exist with a neutron and gain weight by one added neutron. That is an isotope. That is hydrogen 2. In fact, there's even hydrogen 3. Okay, it's still hydrogen. Notice that, but it's unstable, not very stable. Not as stable as hydrogen 2 and hydrogen 1. So the neutron, by adding neutrons, you haven't changed the element, you have created another isotope, okay? And so we're going to get into, let me see if I can push. Do we have enough for carbon? Okay, here's carbon. Okay, by itself, I'm going to take all the neutrons out. No, I'm taking it here. Let me pull the neutron out. Now, carbon has a total of 6 electrons. Oh, notice when I grab an electron and bring it in the inside, it goes to the outside because the first layer of electrons is full. We'll have more about that, and it goes to the next layer. That's where it goes. If I check the stability, carbon without neutrons is extremely unstable. And so I got to add some neutrons in there. 2, 3, 4, 5, 6. Okay, so this carbon 6, which is the most common stable, the most common isotope, very stable. This is carbon 12. Okay, notice the mass number here. What I got? I'm missing 2. Oh, I'm missing 2 electrons, and I got a charge there. All right. So carbon has 6 protons. Look it up here in the far left. 6 protons, 6 neutrons, and 6 electrons. Okay. That is the most common isotope. That's carbon 12. I put in 1 neutron, I make carbon 13, which is still carbon, it's just another isotope. Okay. And I make carbon 14, which is a little bit unstable. Okay. Well, anyway, with that, yeah, this is a good way to learn about how the atoms are put together, okay, with respect to the subatomic particles, get a better picture. And we will continue next Friday, and I'll finish up this chapter and jump into chapter 4. If you have not taken the exam, good luck. Keep it simple. Read the instructions. Don't make. I'm not trying to confuse you or anything like that with respect to the questions. I think they're pretty straightforward. But take your time and knock it out, and give you your best shot. There are 2 questions that I need to manually grade, and so you won't see your full test score until they're all, until those are graded. So I'm waiting until everybody's done, and I'm gonna go in there and grade everybody in one shot. So I should have that done by Sunday for sure, no problem. Okay. Any